This is Lab 6, Magnetic Molasses by Bahrainian. So to introduce this lab, our purpose was to study the principle of electromagnetic induction by analyzing the EMF created in an aluminum tube by changing magnetic flux caused by a bar magnet in free fall. Our materials were a bar magnet, magnetometer, sensor, aluminum tube, and glow script. System was the bar magnet and aluminum tube. Surroundings was everything else. And our measured time was 1.462 seconds, and our calculated time was 1.22 seconds. These are the fundamental principles used in the lab. We had the Biot-Savart law, which says the magnetic field due to a charged particle is dependent on the particle's speed, charge, and distance from the observation location. And Faraday's law that says the EMF generated in a closed boundary curve is the negative rate of change of a magnetic flux through the surface enclosed by that boundary. So this is our experimental procedure. We used the magnetometer app on the smartphone and identified the north and south poles of the bar magnet. Secondly, we dropped the bar magnet with the north pole facing down through the aluminum tube and measured the time it took to exit the tube from the time it entered. We repeated this process about 5 times to get the average time. So when trying to collect data regarding our system, we found that the aluminum tube has a length of 47 centimeters, inner radius of 3.3 centimeters, and outer radius of 4.5 centimeters. The bar magnet had a mass of 0.027 kilograms and a magnetic dipole moment of 4.724 meters. So this is our GlowScript code. Using GlowScript, we were able to computationally model our results. These first functions on the right allowed us to calculate the magnetic field made by the bar magnet and magnetic flux due to the magnet. Furthermore, we used these functions on the right to find the magnetic force due to the bar magnet on the tube. As you can see, the gravitational force and magnetic force were used to ultimately find the net force. So this is our two computational models. As you can see, they are both videos, but I were not able to import those, so instead I used some pictures. Just know that the pictures varied with time. As you can see, the bar magnet falls with increasing speed at first, then slows down and falls with constant speed until it exits the tube. Okay, so let's get into some analysis questions. Well, which color corresponds to the clockwise current and which is the counterclockwise? Red corresponds to the counterclockwise current and blue corresponds to the clockwise current. The magnet is falling with the dipole moment acting downwards, meaning that flux is increasing below it and decreasing above it. Because of Lenz's law, the induced electric field, which is in the same direction as the current, produces an EMF that created current so that it can resist changes in flux. What happens to the dynamics of the system when you flip the magnet around? Well, the magnet would fall the exact same way, but the directions of current would be swapped due to the magnetic dipole moment vector pointing in opposite directions. How does our time in real life compare to our computational model, and how can we make it more accurate? Well, the time in the tube is 1.426 seconds, which is fairly close to our measured time of 1.22 seconds. The computation uses time steps, meaning it does not account for the full situation. Furthermore, there are many errors such as keeping the dipole moment perpendicular to the plane and human error that could have varied our times. What does the shape of the velocity versus time graph tell us about the bar magnet? Well, it tells us that the gravitational force is greater than the induced magnetic force as the bar magnet enters and exits the tube, while being equal to the bar magnet passing through the tube. Okay, some errors and assumptions. Well, we assumed that there would be no air resistance. The bar magnet had a perfectly ideal magnetic dipole, and other external forces are not acting on the magnet. Some potential errors could have been we inaccurately measured times, thus skewing the average. If the magnet was not dropped perfectly perpendicular to the cross-section of the tube, magnetic flux could be inaccurate, and the magnet could have collided with the tube and thus slowed its fall. Okay, what if the resistivity of the conductor were reduced as close as possible to zero, and how would this change our dynamics? Well, if the resistivity were reduced as close as possible to zero, the induced current would be larger and the resulting magnetic field opposing the changing flux would also be larger. This would cause the bar magnet to fall even slower, increasing the total fall time. What if holes or slots were cut into the tube? How would this affect the ring currents in our model? If holes or slots were cut into the tube, the ring currents in the model would no longer exist at every cross-section of the tube as they do now. Instead, current would only form in regions where the tube is still continuous. This would reduce the overall current in the tube, leading to a weaker induced magnetic field and causing the bar magnet to fall even faster.